This talk is about Intel RealSenses. We use them a lot. But okay, let's put but more formally, I'm going to be talking about Intel RealSenses and Sidewalk autonomy. So here's a little bit about what I'm going to be talking about. Since I've got this glorious opportunity, I'm going to start by talking a little bit about me first. Then I'm going to pitch Marble a bit. Then I'm going to answer the question, sidewalk robots, are they just miniature autonomous cars? And then I'm going to talk about a few of the RealSense applications, namely in AutoCallb, which is our automated calibration tool, in ground estimation and detection of obstacles, both dynamic and static. And finally, how we use them in deep learning and for drivable area estimation. Finally, I'll be talking about a few requests we have with the RealSenses team for the future products with regards to which would make our life in integrating them much simpler. And finally, I'm just going to end with the summary. So let me just start off with a little bit about me. In particular, my journey with cameras for 3D perception. So I was a research assistant at IIIT Hyderabad, and I started, that was my first time, this was about 4 years back, that I started working on spatial transformations and projective transformations. And I eventually started working on using cameras for visual servoing of dual-arm robots in a gravity-free environment. So that was my first taste with using cameras for 3D stuff. Eventually, I started my master's in robotics at the University of Pennsylvania. So there I initially started working with the Baxter first. We had a Kinect that was mounted on top, and we used to use the 3D information from the Kinect to do tasks like pouring liquids from flasks. I also made this, as part of my final year project, I also made this tour bot, which basically moved around the halls of UPenn and gave descriptions about the rooms and the professors and whatnot. So it was there then that I was first introduced to the Intel RealSense, namely the ZR300. So we had to choose between the ZR300 and Kinect, and we obviously chose the Kinect. But it is mostly because we had a lot of trouble configuring the ZR300. So about a year back when I joined Marble, they handed me the RealSense D415, and they told me, you've got to make this work for sidewalk autonomy outdoors. So, I was a bit apprehensive about it, but this talk will basically clear out how wrong I was about the D415s. So a little bit about Marble. So this is our robot, Burada. We're a big cheese company. We love cheese. We name everything with cheese. So this is Burada. What is Marble's goal? So our goal is to achieve, to make intelligent four-wheeled robots that are able to drive autonomously on sidewalks and deliver stuff from parcel to food to prescriptions, you name it. But you might think, why do we need a sidewalk robot? The main answer is to adapt to the change in the way we buy things. About 20 or 30 years back, people used to drive to stores to buy their goods. Eventually, with Amazon, that changed to waiting for a week for your package. And now deliveries are wanted in a couple of hours. So this would essentially mean that delivery companies would be pumping out more trucks to deliver your goods, which would mean pollution both in the noise sense and the air sense. So we want to provide an eco-friendly alternative that can do that. And of course, we also want to help. Those in the disabled community, and also busy parents who can't afford to make that 1 hour or 2 hour trip to the nearest store. What problem are we trying to solve? We're trying to solve the problem of a better last mile. And these are our core principles. We want to make it accessible. We want the local grocery store to be able to compete with the big market stores. And we want to provide them the ability to do that, to be able to deliver to their customers around them. We want to ensure security. We want to ensure that when your parcels go from point A to point B, they reach them. They reach them and nobody's able to pick them up in the middle. We want to be reliable. We want to ensure that your stuff gets in time, and we want to ensure that we make those 2 hour marks that you need. we strive for safety. We are trying to achieve sidewalk autonomy after all. So we want to ensure that we are not that we're safely bypassing pedestrians, and we're taking into account everything that's around us. And for that, we ensure that we're testing. We ensure that we're testing and we are evaluating our systems. And the most important part in achieving that goal of sidewalk autonomy is the sensors we use. The sensors become critically important in that sense. And we achieve that through 360-degree vision. We've got econ cameras, which are simply RGB input cameras, which are around the camera, which are around the robot. We've got about 6 of those, which enable a remote teleop operators to see and gives us RGB data about what is there around us. We've got a Velodyne, which you can see right on the top, which is a VLP16 LiDAR, which is 16 scans, and we get depth information from that. We get very high precision depth information from that. We of course have IMUs and GPS, and of course we have the RealSenses. So we actually have 7 RealSenses on board. So we have the front 4 RealSenses are the most important ones because they play a very important role in our forward driving capabilities, and they're named the left forward, right forward, the front forward, which is tilted a bit up, and the front down RealSense. The left, right, and there's a RealSense at the rear. Those help us find the obstacles that are coming from the side or coming from behind. They help us keep a track of that. But before I jump into how we use the D415 RealSenses, I want to talk about the differences between autonomous cars and sidewalk robots. While they may have the same goal of achieving autonomy to be able to drive on their own, the environments they operate in are very different. So you can see the Waymo car, the famous Waymo car, at an intersection, and that's us at an intersection at the sidewalk. You can see map and the Velodyne cloud basically, and this is how our robot sees the world. So what are the differences between them? Computation power. Autonomous cars have a ton of compute power. We have very low compute power, and that means we need to really think carefully about which algorithms we implement, how we implement them, which sensors we use. All of this is determined by that. We can't just use high-density LiDARs everywhere because we wouldn't have enough compute to process them. Robot design. When you think of a vehicle that needs to operate on the road, you're going to obviously think of a car. So they can use cars as a base and build on top of that. Our hardware team had the challenge of designing a vehicle that could navigate on sidewalks, was easily visible, and wouldn't be cumbersome in a way that that pedestrians might find it awful to deal with, on the sidewalks. So they had that design challenge. In terms of the sensor power available, we can't have a massive battery. Our robots are particularly small, and we have certain constraints when it comes to cooling, and which is why our sensors can't draw a ton of power. While it is not so for autonomous cars, and hence you see them with a bunch of high-density LiDARs surrounding them. Custom-built sensors. Of course, autonomous car companies have a lot more money than we do, so they have the capability of custom designing their own sensors according to what they need. We, on the other hand, prefer off-the-shelf sensors. We would prefer if there was an out-of-the-box solution that we could easily integrate into our system. In terms of the operating environment, you can see that autonomous cars operate on roads. There are traffic signs, there are proper lane markings, and there are intersections which tell you where people might be, and traffic signs, which kind of helps them design their algorithms. We, on the other hand, operate on sidewalks. Sidewalks are much more diverse. I mean, in fact, sidewalks from San Francisco vary a lot from the sidewalks in Santa Clara in terms of pedestrian density, in terms of quality, in terms of texture. And it's really hard to develop algorithms which are robust to these changes. But the main difference is, of course, the operating speeds. Autonomous cars are operating on freeways and on roads, and they have to sense and react very quickly, which is why everything like the high computation power and all of this makes really a lot of sense, because they need to sense and react very quickly. We, on the other hand, are operating at walking speeds. We can deal with a little bit of latency. I mean, that wouldn't bother us a lot. So the next question you can ask is, why do we need near-field sensing? I mean, we've got a Velodyne on top. Isn't that the solution to everything? So this is what our robot, so there's a robot there, and this is the Velodyne cloud it's seeing. And it's tilted downward, so yeah. So there's like a massive empty spot in front of it, and it'll think that, okay, let me just drive. But no, there was a dog sitting in front of it, and it would have run over that dog had it not been for the RealSenses. But similarly, you can think of a situation where a pedestrian is walking towards us, and we're tracking it within the Velodyne, and it suddenly comes into that blind spot, and we lose track of it. I mean, our planner will have no information about how the pedestrian is going to react as soon as it comes into the blind spot. So we did need some form of near-field sensing.
Is that picture on the left an actual image of the thing on the right?
Yes.
Wow.
So you can make out the dog, actually. It's the same dog, and it's in the same pose. So you can actually make out the dog in that. That's the level of detail we were looking for in our near-field sensors. So what is the detail we were looking for in our near-field sensors? What are our requirements? We wanted objects to be seen within 5 meters very reliably, because that is how large the blind spot was, which is pretty high for a sidewalk robot. We wanted to be able to distinguish the ground from small objects. Of course, that's a given. I mean, if you come to San Francisco, there are a ton of tiny dogs, so we needed to distinguish the dogs from the ground. We wanted a minimum usable sensor range within 15 centimeters, which is why we have a RealSense pointing straight down, which gives us an idea of the immediate gradient of the ground right in front of the robot. We wanted the field of view to cover all of our forward driving capabilities, which is why they're placed in the way they are, so that it covers a cone of area where our planner can drive, basically. We wanted motion blur of no greater than 5%. We, of course, this is super important, we wanted it to operate at 10 hertz, which is a frequency of 10 hertz. And most importantly, we did not want it to interfere with our other sensors. We did not want our cameras and infrared cameras to be affecting our Velodyne or GPS and whatnot. It's crazy. Yeah, I think I forgot to mention one thing, but yeah, operating outdoors, it's super hard to find a near-field sensor that can operate outdoors well. But we did find a solution after a lot of testing, and after going through a ton of cameras, we did finally find a solution, which was the RealSense D415. It checked off all of these boxes. So now we had a much better view of the road. So this is just a robot hanging out at an intersection. And you can see as the cycle moves from the Velodyne to the RealSenses, you can actually make out the spokes of the wheels and the gears, and it's absolutely incredible the first time we saw the data from them. So I had talked about 4 RealSenses which were in front, which was the front forward, which is in yellow over here, the front down, which is pointed down, which is the green. So these are 4 different RealSenses that have been meshed together. Yeah, sorry, that's a good point. So these are 4 different RealSenses that have been meshed together, which I mentioned, which contribute to our forward driving capabilities. Yeah, I think the color scheme might change in the future slides, but yeah, that's the idea. So one of the yellow RealSense is the one which is tilted a bit up. The front down RealSense is the green one, which is pointed straight down. So there's one that's left and there's one that's right. So these are the 4 RealSenses that we use for our forward driving capabilities.
You mentioned 10 frames a second. That doesn't look like 10 frames a second.
Yeah, it's been slowed down. Just so that, because the cycle passes by pretty quickly. So yeah, just for visualization purposes. So So yeah, so now let's come to the part of how do we actually use them. So we now went from a single depth sensor system to a multi-depth sensor system. We had, instead of one Velodyne, we had one Velodyne and 7 RealSenses. And we needed to find a way to integrate them all together. And we also wanted a way to, we also wanted to find a way of involving the perception cameras too, our econ cameras too. So we wanted to find a way of where we could easily find the extrinsic calibration or the way the different sensors are oriented with respect to each other, which is why we came up with the system of AutoCallb. So in the setup, what do we know? We knew the physical attributes of the calibration target. We were able to track the position of the robot using our different inertial measurement units, sensors. And we had depth sensors from various sensors, and we had the initial estimate of the transforms from the CAD model. Since everything on the robot was custom built, we had a pretty accurate model of the robot. But that didn't do because, of course, even a 0.1 degree in error will mess up your ground estimation by a ton. It'll just throw up tons of false obstacles. So we needed to have a precision, about a sub-millimeter accuracy precision, and within like 0.001 degrees of accuracy. So using the physical attributes of the robot and the position of the robot, you can get the estimate for the position of a particular point on the target with respect to the robot frame, and using the direct depth estimates, you also have its estimate with respect to the sensor frame. So basically, you have two estimates from the same of the same point from two different orientations, one from direct physical measurements and one from the sensor. So using measurements from multiple points and seeing them from different positions, you can estimate the optimal pose between the depth sensor and the robot frame. And by robot frame, I mean it's a frame on the robot, which could be the center of the axle, for example, center of the rear axle, for example. So you can estimate the pose between the sensor and that robot frame by modeling it as non-linear least squares, which basically, so here RS means real sense. So X super sub RS is basically the point observed in the real sense, and X robot is the point observed from the robot frame. So you basically transform, so for each point, you basically transform that particular point from the sensor frame to the robot frame, and you get and you subtract them, basically. So you get the error in estimate. And you get the error in estimates for multiple points from multiple points of view. You take the L2 norm and square it and add it up, and you find the rotation and translation, which minimizes the sum of squares of errors, basically, and that will give you your optimal pose. So once this was done, we knew how the different sensors were oriented with respect to each other, and we could use them we could actually fuse them for developing our systems. So once we had that down, we decided we'd do some ground estimation. So this is something I collected literally 2 days before, but yeah. So this is how a robot is seeing the world, and this is the robot in autonomy. This is nobody is controlling the robot. This is the robot doing its own things. Just to give you a bit of context first, the individual polygonal blobs you see are people being tracked. The white, and this is on an obstacle grid, so the colors are a ground elevation map. And the white pixels that are being pasted are what it thinks are static obstacles.
What's taking the picture?
Sorry?
What's taking the picture from the top?
Oh, that's our software. I mean, yeah, that's just software just viewing it. Yeah, I mean this is the live animation that we can produce. Yeah.
You have two cameras on top, or?
So these are the two perception cameras, which are so we have 6 RGB cameras, but these are the two front-forward perception cameras. Yeah, just for visualization purposes. We actually have a 360-degree vision view, so yeah, you can see it in any direction. But these are the two front perception cameras that we have.
What's the yellow line on top of it?
Yeah, I was going to explain that. So the yellow line is our planner making updates. As it encounters obstacles. So now it stopped. It had to wait for the lady to pass by, and it makes it. So you can see it's constantly updating with the obstacles it's receiving. So ground estimation involved aggregating data from the Velodyne and the RealSenses together. So we had to weigh them in an accurate manner to make it work, to estimate the ground. But what we were also doing is, as time passes by, the last time when it is seen, we decay the influence of the last data that we saw. Like if the real senses pass by it, basically we weigh data that was seen more recently higher than what was seen in the past. And we also are aggregating data from multiple sensors together to estimate the ground. So yeah, so that's what's involved in ground estimation. I can't go into too much detail. But yeah, so once we have an estimate of the ground, we can use the data from these depth sensors to estimate what's above the ground. So we'll get an idea, okay, in real time that these are the obstacles. But we're also tracking the depth data with time. So using the robot position plus how the depth data is changing around the robot, we can estimate which obstacles are static and which aren't. But okay, now we had a ground estimation, and we had a way of detecting obstacles and bypassing them. But there was one thing we never thought about. We had to tell the robot where to drive. You can imagine a situation where it might cut through somebody's yard just because it has to avoid an obstacle. It doesn't know that the yard is is not a permissible area to drive. Or sometimes it might just go on the road in order to avoid an obstacle. It doesn't know where it can drive. So we decided to throw deep learning at this problem. We decided to say, okay, let's use deep learning to estimate what the drivable area is. But there was a problem. This was really uncharted territory. There is literally no public data set available for sidewalks because there is nothing that moves on sidewalks right now. Ideally, we wanted semantic information like this. We wanted it to have knowledge about what is above the ground, which is pointed out by the yellow, stuff like lampposts and fire hydrants and trees and just these. It needed to have knowledge about what's above the ground. It needed to have an idea of foliage so that it's not going on somebody's yard. Of course, it needed to know what was the road, which is painted in orange. And it also needed to know where intersections were, so that when it encountered towards an intersection, it could tell the operator, okay, you need to be careful right now because I'm going to have to cross the road. So it needed to have these kinds of information. And of course, white is the drivable area. That's what we call the drivable area, the area where the robot is allowed to drive. So we developed a deep learning network. For those of you who don't know, semantic segmentation basically means doing a pixel-wise inference of whether a particular about what class it belongs to. So yeah, so we developed a deep learning network that was able to do semantic segmentation in real time about what the drivable area was. And you can see it works pretty well, for this. And more importantly, we were able to use the depth information from the real senses and to further refine our semantic understanding. So it could tell that it basically allowed us to remove semantic inferences which did not feel coherent with did not seem coherent with the RGB segmentation class that was provided.
Did you have a model for potholes?
Yeah, so that was kind of the previous slide was kind of an example of the kind of labeling data we had to gather. So we had literally robots just driving all day around and collecting images like these from the various RGB and RealSense RGB data. And this was all aggregated and labeled and quality assured. This took a lot of effort to gather this data and actually have something to make it usable for our purpose. Yeah. It does. So streetlights are included, hydrants are included. Anything above the ground, it was trained for anything that was above the ground, like trees and fire hydrants and light poles, anything of like that, it was labeled yellow basically, and it was part of that obstacle grid. In how do we cross the road? Right now, the simple answer is the robot doesn't on its own. It will detect that a sidewalk has come, that an intersection has come. It will tell a remote teleop operator that please take over. It will take over for that instance, and then it will go on, proceed with its autonomy. So yeah, that's it. Anybody?
Yeah. Does that mean for every neighborhood you wanted?
Does that mean for every neighborhood you want it, you have to train it for that?
So amazingly, no. I mean, yes and no. It's like with every new region we went to, so this algorithm was tested in San Francisco, Concord, and in Arlington, Texas. So when we went to Arlington, Texas, we had the same question you had, that, will we have to just redo this again and implement everything? But it actually proved that our algorithm was robust enough that we just fed some data from Texas Arlington into our already available data set, and it worked out pretty well. So yeah, I mean, that was part of our requirement, be robust to different regions.
Is there a GPU installed on
Yes.
on the robot?
Yeah.
And one final question: have you open sourced the data set?
No. It took a lot of money to make this, so no.
Do you guys use depth information?
Yeah,
Depth information for semantic segmentation, or is it just?
No, so we just use the depth data to refine our understanding. I mean, yeah, some things like maybe off the top of my head, shadows can be eliminated using the depth data, because that point corresponds to something in the depth data, so we can kind of remove it. Yeah.
Hey, did you consider using stereo vision just from cheap RGB cameras, and if so, how did that fall flat compared to the RealSenses?
I mean, I wasn't there before this. When I joined, the RealSense were handed to me. They were, yeah. I mean, the part of deciding the near-field sensor done before me. But I think, yeah, I think the RealSenses provide us an out-of-the-box solution, and I think we just went with it. It's hard for a startup like ours with limited number of people in the team to kind of refine stereo vision to work outdoors. It's really hard finding sensors that work outdoors well, and that's why a lot of people you'll see, use velodynes or ultrasonic sensors. And yeah, it's really hard to find visual sensors that do that. Yeah.
I have a business-related question. First is, what's the business model for your company? Also, I'm curious, like for now, I see you have managed 7 sensors. I think the cost probably not that cheap. I'm curious, like for now, what's the cost level you can cut for one?
Yeah. So when you talk about the RealSenses are pretty cheap. They're $150 maybe a pop. And I think cheaper when you buy them in bulk, maybe, I don't know. But $150 isn't a lot when it comes to sensors. Like the Velodyne puck on top, I think used to cost about $12,000 when we used to do. Yeah, so we're actually, yeah, cost is definitely part of it, because again, as I said, we're a small startup with a limited budget. So the RealSenses fit our bill in that way. It's like, they gave us the near field sensing we wanted at a cheap cost, and we also had Intel support. So, yeah.
Just one more question on this side.
Yeah.
Do you handle different weathers?
Sorry, weathers? As of now, the rain, no. No. We are still working on it, but right now with this prototype, no. But that is part of our future releases, of course. Yeah, no precipitation right now. Yeah. So once we had an online drivable area estimation network, we thought we should also add some kind of redundancy, because a deep learning network can't be expected to work every single time it moves out, because light conditions vary and the area it's traveling in varies. So what we did was, during our mapping procedure, we ran a different deep learning network that was more that was deeper and that was kind of more refined, and we ran it during a deep learning network, and we basically painted the sidewalks. And this gave us the redundancy that we were looking for. So when the robot, so as you can see in this image, the green is the prior drivable area knowledge that we have, and this was also this wasn't static. This was getting constantly updated. So if a tree was planted and then uprooted, it would be reflected if we came across that area again. But we had enough redundancy in our drivable area in estimation that we could be safe about it. We thought it was safe in a way. Yep. The final thing with respect to deep learning that we were using it for was colorizing our maps for data labeling and evaluation. These drivable area, the database of offline drivable area that we had, it was being quality assured by our operations team, and it's really hard for them to look at regular map and tell if the semantic network worked well or not. So we color our maps to so that's easy for them to match those to match up the predictions with real RGB data. It also but labeling the map also gives context to labeling companies to be for them to be able to label our data correctly, which we use for evaluating a perception algorithms. So basically, we generate data, we generate raw data, we provide it to labeling companies, and it's labeled by humans. We pass this raw data also through our prediction system, and we evaluate it. We evaluate it by comparing the predictions we made versus the predictions that humans made, which is also treated as ground truth. And we use those insights. To improve our system. So it's a continuous feedback loop. So we use labeling for that purpose, for evaluating our perception algorithms, so that we have a ground truth to compare our perception results with. But yeah, this is what our philosophy for improvement is. So this is kind of the entire system in action. So there are no smoke and mirrors. This is how our autonomy usually looks like. It gives pedestrians enough space. It stops for politeness. And our team has done a really fantastic work with the Velodyne and, of course, the Intel RealSense's data available. And they've done a terrific job in making all of this possible. But of course, as with any out-of-the-box solution, there's always issues with integration can't be smooth. We are using an out-of-the-box solution in our robot to develop a product. We are using a product to develop a product. So these were a few challenges we faced when we were working with the RealSenses. One was, of course, the firmware libRealSense and RealSense ROS driver configuration. Like, we had to experiment a lot to get it in a stable configuration. More insight about how it behaves in different lighting conditions would have also really helped us. A lot of the use cases for the RealSenses that I've personally seen have been indoors, and more insight about how. So initially with the default configurations, we weren't getting good results, and we had to manually tune it to get it in a good working condition outdoors. Time syncing is super important for us. Time syncing with a central time system was a top priority for us, and I guess with future updates, we were able to make that possible too. A constant update on important fixes. Another important feature that we were looking for was auto-detecting failure and being able to handle it gracefully. So our robots are operating in the field for like 6-7 hours straight, and a RealSense dropping out means we're driving blind. So we wanted it in a state where it was reliable and stable. But yeah, I mean, of course, as with any, in the future, we are definitely gonna, we have much better knowledge of, how to work with the real senses and what are the different pieces of the puzzle. And Intel support has been super, super amazing in helping us through all of this stuff. I mean, it's only after their help that we've been able to, make it so stable and reliable. Yep.
So you said that you have to do some manual adjustment for the exposure for outside. Do you guys have a real-time auto exposure that's constantly adjusting exposure, or is it you set it and then you run all day?
So there were, besides the exposure, there were different configurations. For the exposure, I think the RealSense already has an auto exposure capability. Yeah.
Is that one, or did you guys run your own?
So I think we made changes that enabled the auto exposure by default. There were some issues we were facing where the exposure would and wouldn't turn on, and so I had to play around with that to make sure that, on startup it was fine. Yeah.
Question?
Yeah.
So how are humans responding to the little robot sharing that sidewalk?
Very good question. So, the kids love us. Kids love us, and people love us. Even in the previous video, you see the 3 people who were there stopped, stared, took out their phone, and took a video of it. So, people really enjoy it. Of course, people have concerns, and we are trying to address them, which is why our company has totally pivoted on making sure we're developing a safe product, we're developing a safe robot.
There have been instances of people attacking robots. Right?
Yes, they have. Yes, they have. And I think it changes with time. It's of course people are going to be comfortable that some of their space is being encroached, but I guess we're trying to develop a robot that's basically, I like to say that we're developing a robot that eventually has to become invisible. It has to become so ingrained in your society that people eventually ignore it. So yeah.
To connect the 7 RealSense cameras, are you using several USB hubs or 7 independent USB?
Yes, we are using several USB hubs.
Like hubs, how many independent controllers are you going to use?
I can't go into the details for that, sorry.
I noticed that the black yellow line is not always straight, and also from your video it shows the robot walking is like all over the place.
Yeah.
It's kind of strange to people that cause a problem.
Yeah, so in that case at least it was, so when it sees an empty road, it tries to center itself. The planner is looking way far ahead. The Velodyne data extends pretty far out. So it tries to plan taking that into account. Of course, we're making improvements to our planner, and it is giving a large leeway to pedestrians right now. We want to, safety is priority, so that's why we are making sure that we're giving pedestrians and any dynamic object enough space to, pivot around.
So I had a question. You mentioned the RealSense provided you the SLAM and the depth data. Can you comment a little bit about what you use for the real-time semantic segmentation and then how you
So every feature I talked about today everything was in real time. So we're using them for our ground estimation stuff and our obstacle detection, and it's the RGB data and the depth data is also being used for estimating the drivable area. So yeah, all of the the real senses we are mostly using the real senses for real time purposes.
One last question.
Yeah.
You talked a lot about planning. What about unexpected events? For example, in your video you showed a jogger approaching the robot.
Yeah.
What if a jogger is coming by the robot from the back and suddenly appears without any planning? How does your robot handle that situation?
So for now we have a chaperone who is constantly monitoring the robot. We have a chaperone per robot, and in case of situations like that, right now our robot will be taken over in that instance. Whenever situations are unexpected or very dangerous, we have an operator who is on field who is taking care of the robot right now. Yeah, until we get those unexpected circumstances in our algorithms, there is going to be a person who's going to be accompanying it. Yeah, so we have a massive and excellent operations team who who are working but toiling really hard and making sure that everybody's safe around the robot. Yeah. Just to summarize, we're Marble Robot. We're trying to provide a better last mile problem through sidewalk autonomy. The problem, I hope we agree now that the problem of sidewalk autonomy is considerably different from the autonomy of cars. The RealSense D415 has been incredibly amazing. It has solved our the huge blind spot that we had in front of a robot, and it's helping us detect obstacles, and it's helping us with segmenting out our environment to tell the robot where it can drive. So yeah, the RealSenses have been super helpful for us in in developing our navigation systems. So from everyone at Marble, I'd really like to thank everybody at Intel, thank you guys for attending the talk. I hope your next meal gets delivered by our robot someday. Yeah. Yep.
Any last questions for Richard? Oh, several. Okay, we'll have about 3 minutes for questions, and then we'll take.
Sure.
Over here.
Yeah.
Hi. In terms of the calibration that you do as the robot is walking, do you lose the calibration or
of course.
The accuracy deteriorates? So how frequently do you have to recalibrate?
So we do have robot maintenance quite frequently. I don't have concrete numbers. I think that's handled by our operations team. But yeah, we do that. Robot maintenance certainly involves recalibrating the robots because, of course, things shake, hardware shakes. So everything loses focus and everything just, yeah. So.
And in terms of the RealSenses, I saw like 4 in the front, right?
Yeah.
And 2 on one side, and maybe there's 1 on the back.
1 left, right, and 1 at the back, yeah.
Oh, okay. So I thought I saw 2 on the left side. I was wondering why there is none on the right.
No, there's 1 on the left, 1 on the right, yeah.
Any question?
Over here?
Oh, yeah, sorry.
Have you guys considered using GPS maps like Google Maps or something for a priori information about sidewalks or any 3D?
I mean, Google Maps aren't really accurate here. We're talking about, mapping it to so each of those blocks that you saw were about 3 centimeters each. So I think it's all about accuracy, mostly.
What I mean is that you could use it at least to see
yeah.
where the roads are and mask out individual locations.
Yeah, we actually use Google Maps to kind of find that corresponding location and make sure things make sense. Yeah. Yep. Yeah.
Yeah? Oh, okay. A question about the Velodyne. It seems to be a big cost driver for your total system.
Yeah.
And now you've come this far. I was wondering, because you know now much more about the sensors and you have other sensors taking over the short range, do you think you can replace that Velodyne by a cheaper version, for instance, the RP LiDAR, or that's only $300?
I mean, Velodyne for all its, for even besides the fact that it gives us a blind spot and the data is not as dense, it is incredibly accurate. It's super accurate at extremely long distances, and we need that. We need that amount of accuracy at that distance for our planner to operate well and be able to, make its decisions. Yeah. So a Velodyne is still super important for us.
Last question.
Yeah.
Hello. I was wondering if you could talk a bit about why you have a preference for the D415 over the D435.
Yeah. There was when I joined, I was given the D415. I'm not exactly sure what the answer was, but yeah, I think the checklist I had, it just crossed, it checked every mark off. So.
I can actually answer to that question. So the D415 has slightly narrower field of view. So actually, Philip will talk about it. I just realized I don't want to spoil your slide. But the D435 has a rolling shutter, which is more typical for Velodyne. Yeah, that's right. So if you're talking about having a fast rotational pose, then yeah, you'd want to use a global shutter. But I think in your case, it's probably safe to go with a global shutter for fast-moving sensors. But in your application, I'd assume that it's not too fast that you get away with the rolling shutter.
One other quick question, if you don't mind. Are you utilizing all the cameras in USB 2.0?
Are we, sorry, can you repeat the question?
The cameras, are they all being utilized in the RealSense cameras? Are they all being utilized in USB 2.0 configuration as opposed to the USB 3.0?
I am not exactly sure about that. I have to get back on that. Yeah. Thank you.